In this video, we're going to talk about big omega and big theta notation. Now, I do want to mention, you're not going to really do many problems on big omega and big theta in the homework, but the theory is important for us for the next section. So I do want to go through it, and we're not going to spend a ton of time on this because I'm just going to be using this theory in our next set of notes. Okay, so let's just talk about it. It's building on the ideas that we've already discussed with big O notation. So let f and g be functions, either from the set of integers or real numbers to the set of real numbers. We say that f is big omega of g of x if there are constants c and k, where the absolute value, oops, just want to make sure I've got a good color, there we go. The absolute value of f of x is bigger than or equal to c times the absolute value of g of x whenever x is bigger than k. So it's the reverse notation. Big omega is giving us a lower bound, where big O gave us an upper bound, okay? So we are working with a lower bound. And that's what I just said right down here in this note. I was like, did I make a note of that? And I did, yay, okay. So big O gives an upper bound, big omega gives a lower bound. Okay, so here's useful information for us. It follows that f of x is big omega of g of x if and only if g of x is big O of f of x. Okay, so what that means is if we happen to know that g of x is big O of f of x, it's going to immediately follow that the reverse would be true, that if g of x is going to be smaller than f of x, we can find some constant to multiply f of x by, then it follows that the reverse is going to be true because this is written in lower bound notation, whereas the other one's written in upper bound notation. Okay, let's go ahead and do a couple examples with this, or actually maybe one example. Yeah, one example. Okay, so show that f of x equaling 8x cubed plus 5x squared plus 7 is big omega for g of x. Okay, so we want to find a constant that this thing is going, the f of x is always going to be bigger than. Okay, so 8x cubed plus 5x squared plus 7x, I'm sorry, plus 7 is clearly going to be bigger than or equal to 8 times x cubed. Okay, so that's this side. Here, let me switch colors. And then this is there's our c right here. That's c. And then this is always bigger than or equal to 8x cubed because these numbers are always positive. So I'm taking a number, which could have some negatives, and then I'm adding positive numbers to it. So the left-hand side is always going to be bigger than the right-hand side, always. So this is true for all for all positive numbers. It's actually true for everything. But the minute we get bigger than 0, it's good. So you could just say that x is bigger than 0, and that is k. There's k. So there we have c, there we have k, and we're done. It's big omega. Okay. Let f and g be functions from the set of integers or real numbers to the set of real numbers. Let the function f of x is big theta. So that is a capital theta, that circle with the funny symbol in it. Okay, that's capital theta, the Greek letter theta. So that's true if and only if f of x is big O of g of x and f of x is big omega of g of x. Okay, we say that f is big theta of g of x and f of x is of order g of x. So we say, I want you to see this phrase here, f of x and g of x are of the same order. So that's a phrasing they're going to use in the last theorem, and I want you to be aware that that's tying to big theta notation when f happens to be big theta of g of x. Or another way of saying that is that f is big omega and big O of g of x. Okay, but here's where it boils down. Here's the useful part. F of x is big omega of g, I'm sorry, big theta of g of x, if and only if there exists constants C1 and C2 and a magical K such that C1 times g of x is less than f of x, which is less than C2 times g of x for x bigger than k. In other words, we're able to trap f of x between constants multiplied by g of x. We're able to trap f of x between them. That is what we have to show. And it's not as hard as it seems. So just to comment on this could be like a large whole number, like 100. And this could be a small fraction, like 1/2. Okay, like the idea is we need to have this function that allows us to kind of trap it like this between example to show this. Okay, so show that the sum of the first positive integers is big theta of n squared. Okay, so what we're trying to show is that if we add up the first integers, dot, 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 down to n, it's going to be trapped by some multiple times n squared and some multiple times n squared below. So both sides, okay? That's what we're going to try to find. I'm going to deal with k in just a minute, but let's first deal with the one-sided. Okay, so we actually already showed this in a previous example. Okay, I'll just redo it really quick. This says that if this is the sum we're looking at, I could say that all of these numbers then would be smaller than or equal to n if I make all of them n, right? Which this is, there's n numbers here, n terms, and there's n of them. So that's n squared. So there we go. We showed that this is less than or equal to n squared, assuming then that c equals 1, or C2. We'll call it C2 since we're working with two c values here. C2 equals 1. All right. And that would be true for all n bigger than or equal to 1. So k is 1. Okay. Or you could say 2 to be safe, because after the first number, we're good to go. Okay, let's go the other way now, the other direction. So we want to show that 1 plus 2 plus dot, dot, dot is bigger than or equal to something with n squared. Okay, so here's how we do it. It's very tricky. We're going to actually use half the number of terms. So right over here, we know that there are n terms. Okay, I'm going to do half terms. So I'm going to start at whatever n over 2 is. Okay, for just a moment, we're going to assume n is even. Okay, just assume n is an even number just to make our life easy. Okay, you cut n in half, whatever number that is. I'm going to start at that number and then keep adding 1 until I get to n. So I'm looking at the half of the terms, the last half in particular. Okay, the last half of the terms. So clearly that's smaller, right? Because we're only looking at the last half of the terms. All right, now we can make each of these n over 2. Every term over here could be thought of as n over 2. So kind of using the same trick we used earlier where we made them all n. This time we're making them all n over 2 because we want them smaller. So clearly that number is smaller if I make all of them n over 2. So how many of these terms do we have? We have half the number of terms. Or in other words, we have n over 2 terms. So if we have n over 2 terms, and they all are n over 2, we have n squared over 4. And there is our C. C is 1/4. And this works again for, or here, call it C1. And this works again for K equaling 2 or more. 1 or more, I think, but 2 or more definitely. Okay, real quick, I said assume n is even, and I just want you to see that this would actually work even if n is odd. We'll just use the smaller half. If we have to cut the terms in half and you can't cut it in evenly, use the smaller half, okay? Or however it gives us to n over 2 terms, whichever one's that smaller one. And since I went ahead and made this, like if this happened to have been n over 2 plus 1 terms, if that happened to be the case right here on this line, if we're working with an odd number and there was a plus 1, there's one extra term, because I used this symbol, it holds. Because I went ahead and assumed, oh, okay, assume smaller number of terms then. Like go one less and we're safe. All right. So if it's odd, we can make it safe. If it's even, which is easier to think about, we can set up this inequality and we'll be good. So there we go. We did it. We trapped the sum on both sides by a constant multiplied by n squared. So we've done it. We've shown that that is in fact big theta. Okay, let's try another one. Let's try another one here. Let's try this. Okay, we want to show that 3x squared plus 8x times the log of x is big theta of x squared. So we need to trap it on both sides. Okay, we're going to try to find a value that this thing is less than C2 times x squared. Okay, we're going to try to find that, and then we're going to do the other side. We're going to try to find a value that's bigger than. Okay, so let's start with this. This one's a little bit more obnoxious. So here's what I want to do. Log is annoying. So let's focus in on log. Okay. Log. All right. So it would be really nice if I could say that the log of x, like, wouldn't it be nice if I could call that just x? Because if I called this x, then I would have 8x squared, right? Because that's 8 times x, 8x squared, and that's 11x squared. So that would work. So what would be really nice is if this statement is true. If I could say that log of x is less than or equal to x, and it actually is true. And here's why. Remember what log is, right? Log is, exponent notation. So if I change this to exponent form, exponential form, this is 10 to the x is less than or equal to, I'm sorry, I did that backwards. If I did it as an equal to sign, log 10x equals x. So here, changing it to exponential notation, sorry, 10 to the x equals x. Oh, okay. So if this is our statement, this would be true. Sorry, I'm just changing it to log form and I'm doing a terrible job. The truth is that if we're looking at those two, x is clearly less than or equal to 10 to the x. Clearly, right? Because if x is 1, I do 10 to the 1. Clearly, that's a bigger number. Okay. So if I take the log of both sides, the left side simplifies to x because log of 10 is just 1. And we could bring the x down. So we did it. We showed that this is true, which means, here's the bigger conclusion now. That means that 3x squared plus 8x times log of x is less than or equal to 3x squared plus 8x squared. So I'm substituting, I'm saying log of x, I'm plugging in x in for there. And that is 11x squared. So there it is. There's C2. We did it. We found C2. Okay, C1 is really easy because it's easy to trap this on the other side. 3x squared plus 8x log x, showing that this is bigger than something times x squared. Okay, so here's the magic one that's going to work, 3. Because 3x squared is going to always be less than this, since we're working with positive numbers for the most part on these anyway. So this is always going to work. Clearly, this is true because I'm adding something to 3x squared on this side, right? That's being added on in addition to 3x squared. So there's C1. And so this is true the minute we are looking at positive x values. So when x is bigger than 0, so that's k. This works too for when x is bigger than 0. So there's k as well. Okay, so we're good for that value. All right. Here's our final theorem, and it is kind of a useful theorem. It basically says that if we're working with a polynomial, the x to the n, the leading term, the coefficient, that is the order. That is that connection to big theta notation or big O notation. In other words, we're able to say that x to the n is big O for f of x, and f of x is also big O for x to the n. We're able to trap it on both sides. So that's the case for any polynomial. We can just look at that leading coefficient. If it's an x cubed is the magic number that's going to work for the theta. And there you go. That's it.